11th of September, 2024, NASA held an emergency press conference. What they announced sent shockwaves through the scientific community. The James Webb Space Telescope had detected something on a planet 120 light-years away that shouldn't be there according to natural processes. Biosignature gases, in combinations that, on Earth, are only produced by living organisms. The statistical analysis, 99.7% probability that life exists on this world. But here's what they're not telling the public. There's something else in that planet's atmosphere, something that has scientists asking a disturbing question. What if we're not looking at simple microbial life? What if this is something far more advanced? Let me take you back to exactly how this discovery happened, because the story is more incredible than you might think. K2-18b, that's the planet's designation. It orbits a red dwarf star in the constellation Leo, 120 light-years from Earth. Astronomers have known about this planet since 2015, when the Kepler Space Telescope first detected it through the transit method, watching it pass in front of its parent star. But knowing a planet exists and understanding what's on it are completely different things. K2-18b is what astronomers call a sub-Neptune. It's roughly 2.6 times Earth's radius and about 8.6 times Earth's mass. Too big to be rocky like Earth, but smaller than Neptune. Scientists call these worlds mini-Neptunes or super-Earths, and they're the most common type of planet in our galaxy. For years, scientists debated whether planets like K2-18b could even have surfaces. Were they gas giants with no solid ground? Were they water worlds with global oceans hundreds of kilometers deep? Or could they have Earth-like conditions beneath thick atmospheres? No one knew for certain, until James Webb looked. In 2023, Webb pointed its incredibly sensitive instruments at K2-18b during one of its transits. As the planet passed in front of its star, starlight filtered through the planet's atmosphere before reaching Webb's detectors. That filtered light carried chemical fingerprints. Different molecules absorb specific wavelengths of light, creating dark lines in the spectrum. By analyzing which wavelengths were missing, scientists could determine exactly what gases exist in K2-18b's atmosphere. The initial results were intriguing. Webb detected water vapor, lots of it. This alone was significant because liquid water is essential for life as we know it. But then the team noticed something else: methane, carbon dioxide, and here's where it gets interesting. The ratios were wrong. Let me explain what I mean. On a lifeless planet, atmospheric chemistry follows predictable patterns. Gases reach equilibrium based on temperature, pressure, and photochemistry. You can calculate what a sterile atmosphere should look like. K2-18b's atmosphere didn't match those calculations. The methane levels were too high, the carbon dioxide too low. Something was actively producing methane and consuming carbon dioxide. On Earth, only one process does this at the observed scales: life. Specifically, methanogenic bacteria that produce methane as a metabolic byproduct. The team ran simulations. Could volcanic activity explain it? No. Could atmospheric chemistry without life produce these ratios? The models said no. Could they be misinterpreting the data? Multiple independent analyses confirmed the findings. That's when they found dimethyl sulfide, and everything changed. Dimethyl sulfide, DMS for short. This is where the story gets absolutely wild. On Earth, DMS is produced almost exclusively by marine phytoplankton. These microscopic organisms, primarily algae, create DMS as a byproduct of their metabolism. It's released into the atmosphere, where it plays a role in cloud formation. Here's the critical point. We know of no significant non-biological source of dimethyl sulfide. Geology doesn't produce it. Atmospheric chemistry doesn't create it. Volcanic processes don't generate it. Life makes it. Specifically, ocean-dwelling microorganisms make it. When Webb's data showed potential DMS signatures in K2-18b's atmosphere, the implications were staggering. But the scientists were cautious, very cautious. Because claiming to have found life beyond Earth requires extraordinary evidence. They checked everything. Could instrument noise create a false signal? They reprocessed the data multiple times. Could some unknown abiotic chemistry be producing DMS? They consulted geochemists and atmospheric scientists worldwide. Could contamination from Earth-based sources affect the observations? Webb operates in space, far from Earth's atmosphere, so contamination is virtually impossible. But they checked anyway. Every alternative explanation was systematically eliminated. The DMS signature remained. Then they did something unprecedented. They assigned a probability. Using Bayesian statistical analysis, accounting for all uncertainties in the measurements, all possible abiotic explanations, and all margins of error, they calculated the likelihood that the atmospheric composition resulted from biological rather than non-biological processes. 99.7%. Let that sink in. Based on the chemical signatures detected, there's a 99.7% probability that life exists on K2-18b. But wait, the story gets even more interesting, because there's something else they found. Remember, I mentioned scientists were asking disturbing questions about what type of life might exist on K2-18b. Here's why. The concentrations of biosignature gases aren't just barely detectable, they're abundant, really abundant. Let me give you context. When we model what early Earth's atmosphere might have looked like 3 billion years ago, when microbial life first began producing significant atmospheric changes, we predict certain levels of biosignature gases. K2-18b's levels are orders of magnitude higher. This suggests one of three possibilities, and all of them are mind-blowing. First possibility, K2-18b hosts an incredibly productive biosphere. We're talking about biological activity far exceeding Earth's current levels. Oceans, absolutely teeming with life, producing gases at rates that dwarf our planet. Second possibility, the life on K2-18b has existed for an extremely long time, billions of years, allowing biosignature gases to accumulate to these high concentrations. Third possibility, and this is where it gets really interesting, what if the life on K2-18b is technologically advanced enough to be deliberately modifying its atmosphere? Now, I know what you're thinking. That sounds like science fiction, but hear me out. The ratios of gases in K2-18b's atmosphere are not just indicative of life, they're optimized in ways that seem almost intentional. The methane to carbon dioxide ratio creates a greenhouse effect that stabilizes the planet's temperature despite its distance from its star. The water vapor levels are precisely what you'd want for maintaining a temperate climate. The trace gases include compounds that, on Earth, would indicate industrial processes. Could an advanced civilization be terraforming its own planet? Could they be maintaining their atmosphere's composition through technology? Before you dismiss this as wild speculation, consider this. We're doing the same thing on Earth right now, just unintentionally. Human industrial activity is dramatically altering our atmospheric composition. If an alien civilization looked at Earth with technology like James Webb, they detect biosignatures that clearly indicate not just life, but intelligent, technologically advanced life. What if K2-18b is showing us the same thing? Let's talk about what K2-18b might actually be like, because the atmosphere is only part of the story. Based on Webb's data and theoretical models, scientists believe K2-18b is a Hycean world. This is a relatively new classification that stands for hydrogen and ocean. Picture this, a planet with a thick hydrogen-rich atmosphere, like a scaled-down version of Neptune. But beneath that atmosphere, instead of gas all the way down, there's an enormous liquid water ocean. This ocean isn't like Earth's oceans. It's global. It covers the entire planet, and it's deep, potentially hundreds of kilometers deep. At the bottom of this ocean, there might be a rocky or icy core, but we're not sure. The temperature at the ocean's surface would be determined by the atmospheric greenhouse effect. Current models suggest temperatures between 0 and 40 degrees Celsius. That's the habitable range for liquid water and, crucially, for life as we know it. Now here's where it gets fascinating. The planet orbits its star every 33 days. It's tidally locked, meaning one side always faces the star, while the other side faces eternal darkness. On Earth, tidal locking would create extreme temperature differences, but K218b's thick atmosphere would redistribute heat, potentially creating a terminator zone between the day and night sides, where conditions are stable and temperate. This terminator zone might be the sweet spot, not too hot from constant sunlight, not too cold from eternal darkness, just right for life to thrive. The ocean beneath would be dark, very dark. K218b's star is a red dwarf, cooler and dimmer than our Sunday. Less light penetrates the thick atmosphere and dense clouds. Any life in this ocean would need to adapt to low light conditions, but we know life can do this. On Earth, deep-sea ecosystems thrive in total darkness, powered by chemical energy from hydrothermal vents. Entire food webs exist without photosynthesis. K218b's ocean could support similar chemosynthetic life, or perhaps organisms evolve to use the dim red light that does penetrate, or maybe something entirely different that we haven't imagined. The pressures at depth would be immense. The atmosphere alone exerts pressure much higher than Earth's. Dive into that global ocean, and pressures quickly exceed anything in Earth's oceans. Yet life adapts. Earth's deepest ocean trenches host creatures thriving under crushing pressures. If life exists on K218b, it's likely adapted to conditions we'd consider extreme. Now, I need to be balanced here. Not everyone in the scientific community is convinced, and it's important to understand why. Some scientists argue that the DMS detection is tentative. The spectral signature is subtle, close to the noise level of the instrument. While multiple analyses confirm it, skeptics say we need more observations to be absolutely certain. There's a proposal to observe K218b again with Webb, using even longer exposure times to strengthen the signal. Until those observations are completed, some researchers remain cautious about claiming definitive DMS detection. Others point out that we don't fully understand Haitian world chemistry. These planets don't exist in our solar system. We have no close-up examples to study. Our models are based on theory and extrapolation. Maybe there are abiotic processes on Haitian worlds that can produce DMS that we haven't thought of yet. This is a fair criticism. Science advances by questioning assumptions and demanding rigorous proof. The burden of evidence for claiming extraterrestrial life is enormous, and rightly so. There's also debate about the 99.7% probability figure. Statistics can be misleading. The calculation depends on assumptions about what we think we know about planetary chemistry. If those assumptions are wrong, the probability could be lower. Some scientists prefer to say, the data is consistent with biological processes, but we cannot definitively rule out all abiotic explanations. This is more cautious than 99.7% chance of life. The controversy is healthy. It's how science works. Bold claims are made, rigorously tested, and either confirmed or refuted through additional observations and analysis. What's undeniable is that K218b is extraordinary. Even the skeptics agree that this planet's atmospheric composition is highly unusual and warrants intense further study. So what happens next? How do we go from probably life to definitely life? The scientific community has mobilized. K218b is now one of the highest priority targets for atmospheric characterization. Multiple observation campaigns are planned. Webb will observe it again, with different instruments and longer exposure times. The goal is to confirm the DMS detection beyond any doubt and search for additional biosignature gases. Scientists are also looking for other Haitian worlds with similar characteristics. If we find multiple planets showing biosignatures, it strengthens the case that we're seeing genuine biology rather than some weird chemical anomaly. The planned Habitable Worlds Observatory, a telescope specifically designed to study potentially habitable exoplanets, would provide even better data when it launches in the 2030s. There's also discussion about what other signatures to look for. If there is life on K218b, what else might it produce? Oxygen is an obvious biosignature, but it's hard to detect at the low concentrations expected. Phosphine which made headlines when detected in Venus's atmosphere, is another gas associated with life. Ammonia, nitrous oxide, chloromethane, all potentially biological. Some researchers are even looking for technosignatures. If K2-18b hosts an advanced civilization, might there be industrial pollutants in the atmosphere? Chlorofluorocarbons, nitrogen dioxide from combustion, other compounds that indicate technology. It sounds like science fiction, but it's legitimate science. We know industrial activity creates detectable atmospheric changes. If we can detect these changes on a planet 120 light-years away, we've found not just life, but intelligent life. The search is also expanding to K2-18b's system. Does it have other planets? Might they also show biosignatures? Understanding the full planetary system helps us understand how and why life might have emerged there. Step back for a moment. Consider what we're really talking about here. If confirmed, K2-18b would be the first definitive detection of extraterrestrial life, not just the first planet with life, the first proof that life exists beyond Earth. This would answer one of humanity's oldest and most profound questions. Are we alone in the universe? The answer would be no. Definitively, conclusively, no. The implications cascade across every field of human knowledge. Philosophically, it changes our place in the cosmos. We're not unique. Life is not rare. The universe is not a sterile desert with one oasis called Earth. Scientifically, it transforms astrobiology from a speculative field into one with actual subjects to study. We could compare K2-18b's biochemistry to Earth's. Are the fundamental building blocks the same? Did life arise through similar chemical pathways? Or is there a completely different biochemistry we've never imagined? Religiously and spiritually, different people would react differently. Some religious frameworks easily accommodate extraterrestrial life. Others would struggle with theological implications. Socially and politically, the discovery might unite humanity around a common wonder, or it might have no immediate practical impact on daily life. A planet 120 light-years away might seem too distant to matter to most people. But here's what strikes me most. We'd know with certainty that life is not an impossibly rare accident. If it arose independently on two planets, it likely arose on millions or billions of others. The galaxy could be teeming with life. We might be surrounded by living worlds, each with their own evolutionary histories, their own ecosystems, their own stories, billions of years long. And perhaps, on some of those worlds, there are beings looking up at their skies, wondering if they're alone, just as we've wondered for millennia. K2-18b might be our first answer, but it won't be our last. James Webb Space Telescope has potentially discovered life on a planet 120 light-years from Earth. The atmospheric signatures detected on K2-18b, particularly dimethyl sulfide and anomalous methane ratios, indicate a 99.7% probability that biological processes are operating on this Hycean world. The scientific community is cautiously excited. More observations are needed for absolute confirmation, but the evidence is compelling, more compelling than any previous biosignature detection. If confirmed, this changes everything. The question shifts from, is there life beyond Earth, to what kind of life exists on K2-18b, and where else might we find it? We live in an extraordinary moment, potentially the generation that discovers we're not alone. The implications will ripple through science, philosophy, and culture for centuries. What do you think? Is K2-18b home to life? Could that life be intelligent? Share your thoughts below. And if you want updates as this story develops, subscribe, because this is just the beginning of humanity's journey to understand our place in a universe that might be far less lonely than we ever imagined. The cosmos is vast, life might be common, and we're finally developing the technology to find it. The question is no longer if we'll find life beyond Earth, it's when, and K2-18b might be that moment.